In the Laservision system, the video and audio information are stored on a disc in encoded form. The information on the disc is scanned optically by a Laservision player and then converted into a TV signal suitable for a standard color television receiver. The VLP-830 Laservision semi-professional player offers all the usual Laservision playback features plus remote control. The VLP-830 has been designed for the less demanding disc user, who does not anticipate the need for computer-controlled programs, teletext overlay, or the use of several series-linked players. The Laservision disc is at the heart of Laservision technology. It has a diameter of 30 centimeters and plays at 1500 revolutions per minute. The Laservision reflective spiral track is read optically by a laser beam which is locked onto it. There is no physical contact between the disc and the scanning system, so that it is possible to select any part of the disc rapidly without damaging it in any way. This spiral track is so fine that one hair from your head could cover 30 Laservision tracks. The laser spot scanning the track is so accurate that it is as if you were driving a car through a tunnel at 100 kilometers per hour, with only 1 millimeter clearance on either side and without touching the sides of the tunnel. The spiral track is so compressed that if you could unwind it, it would be more than 30 kilometers long. The information on the Laservision disc is contained in a spiral track which is read outwards from the center. The lens must therefore be moved in the same direction in order that it may follow the track. This is achieved by mounting the lens and all the other components of the optical system on a motor-driven sledge, which moves it under the disc. The laser spot must follow the track with great accuracy. This is realized by utilizing two subsidiary beams. When the tracking is correct, the signals from both beams should be equal, and when it is not, the signals from both beams will be unequal to the extent of the tracking error. The different signal is utilized by the servo system to guide the radial mirror and the sledge. The first component in the light path is the light source that consists of a 1 milliwatt helium neon laser. The light that the laser radiates is monochromatic, coherent, and is linear polarized. The laser beam is fed through the spot lens, causing the beam to diverge, and is reflected through the beam splitter. The laser beam now hits the folding mirror and collimator lens and arrives into the objective slide. Here, the beam is reflected by the radial and tangential mirrors and focused by the objective. The movement of the objective slide is such that the beginning and end of the disc can be scanned. In order to simplify this demonstration, the objective slide, including the disc, is replaced by a single mirror, the disc mirror. The objective focuses the laser beam on the disc mirror, which reflects the beam back along the same path. To achieve a splitting of the beam to the photodiodes, a quarter lambda plate is placed in the light path. The laser beam now hits the photodiodes A, B, C, and D. And finally, the cylinder lens provides the possibility to achieve focus control. If the disc mirror is in focus, then the 4 quadrants are equally illuminated. When the position of the disc mirror is changed, the laser spot changes into an ellipse. Too close to the objective, the ellipse hits the quadrants A and B. Too far from the objective, then the ellipse hits the quadrants C and D. The intensity of the laser beam on the photodiodes can be changed by turning the quarter lambda plate. In a certain position, the intensity will be at a maximum, with the quarter lambda plate turned 90 degrees at a minimum. When the laser beam passes through the grating, several other beams are formed. The position of these beams can be changed by turning the grating in order to achieve correct radial tracking. In the objective slide, the laser beam is first deflected by the radial mirror and then by the tangential mirror. The 2 subsidiary beams, which are used for tracking, generate an electrical signal via the photodiodes R1 and R2. When the tracking is correct, the intensity of the light spots on R1 and R2 are equal, resulting in the difference signal being 0. When the tracking is incorrect, the intensity of the light spots on R1 and R2 will be unequal, resulting in a difference signal which is always proportional to the degree of tracking inaccuracy. This is then fed to the servo system to apply the necessary correction to guide the radial mirror as a continuous correction process. Guide the radial mirror as a continuous correction process. Necessary correction to guide the radial mirror as a continuous correction process. To guide the radial mirror as a continuous correction process. System to apply the necessary correction to guide the radial mirror as a continuous correction process. First, we have the source of light, a small helium neon laser beam, and as you know, a laser beam can be focused very precisely. With the help of lenses and a prism, the light is projected onto the reflecting surface of the disc, on which there are billions of small indentations. The reflected light is converted into electrical impulses. The disc is coated with a protective layer of plastic. The light beam is adjusted. Disc is coated with a protective layer of plastic. The light beam is adjusted with a protective layer of plastic. The light beam is adjusted Disc is coated with a protective layer of plastic. The light beam is adjusted with a protective layer of plastic. The light beam is adjusted coated with a protective layer of plastic. The light beam is adjusted with a protective layer of plastic. The light beam is the target block into position 1 on the deck. Adjust the spot lens until the laser beam fills target 1 completely. Place the target block into position 2. Adjust the folding mirror until the laser beam fills target 2 completely. Remove the objective from the objective slide. Mirror alignment turret into the hole in the jig. Support the objective slide to avoid it moving upwards and adjust the radial and tangential mirrors in the slide until the shadow of the crossed lines lies within the circle on the frosted glass screen. Remove the objective from the slide and place the test jig on the slide guide points above the objective slide. Place the pupil filling meter into the objective holder through the hole in the test jig. The pins on the meter should engage the grooves in the jig. Move the test jig to its extreme position in the direction of the folding mirror. Switch on with the power button and press S1 and S3. Adjust the spot lens until the horizontal lines on the oscilloscope coincide with the 0 line in the best possible manner. Move the test jig to its extreme position in the direction of the turntable motor and adjust the folding mirror until the lines coincide with the 0 line of the oscilloscope as precisely as possible. Repeat the adjustments a few times until the deviation of the two lines relative to the 0 line is not more than 50 millivolts when the test jig is moved to and fro. Remove the pupil filling meter from the test jig and place the mirror alignment turret on the test jig. Adjust the radial and tangential mirrors in the slide so that the shadow of the crossed lines lies within the circle on the frosted glass screen. Optimize the adjustment of the spot lens. Bring the objective slide to a position about halfway under the disc position. Place the 8-inch test disc with its unrecorded side face down on the turntable. Switch on the power button and press S4. Set the frequency of the signal and adjust the power supply and the amplitude of the generator signal so that the objective starts to oscillate freely and an S-curve is displayed on the oscilloscope screen, beam A. Adjust the setting screws of the photodiode so that the amplitude of the S-curve is a maximum. If the minimum value of the voltage, 1 volt, is not reached, the components in the light path must be inspected for dust and other contaminants. Press S3 and adjust the setting screws of the photodiode until the amplitude of the difference signal. Setting screws of the photodiode until the amplitude of the difference signals. Press S3 and adjust the setting screws of the photodiode until the amplitude of the difference signal. And adjust the setting screws of the photodiode until the amplitude of the difference signal. Press S3 and adjust the setting screws of the photodiode until the amplitude of the difference signal. S3 and adjust the setting screws of the photodiode until the amplitude of the difference signal. Press S3 and adjust the setting screws of the photodiode until the amplitude of the difference signal. Adjust the setting screws of the photodiode until the amplitude of the difference signal. Screws of the photodiode until the amplitude of the difference signal. Setting screws of the photodiode until the amplitude equals. Press S2. The sum signal A plus B plus C plus D is displayed on the A channel of the oscilloscope. Adjust the quarter lambda plate using the accessory key so as to obtain a minimal ripple on the peak of the sum signal. Put on the 8-inch test disc and select still picture number 17,000. Unlock the slide drive mechanism by pressing the bracket of the slide motor downwards. Unplug connectors B19 and B20 on the connector panel. Unplug connector B02 on the servo preamplifier panel and insert this connector into B02 of the test lead. Press S4 so that the radial difference signal R1 minus R2 appears on the oscilloscope. Turn the grating screw until the oscilloscope displays the radial difference signal for the 2.5 and 1.6 micrometer track pitch. Manually rotate the gear wheel if necessary. Turn the grating screw anti-clockwise until the radial difference signal is minimal for both track pitches. The position of the 3 spots is now exactly in line with the tracks. Press S2. The radial sum signal, R1 plus R2, is now displayed on the oscilloscope. Move the objective slide until approximately picture number 16,000 is displayed. Track pitch 1.4 micrometers. Turn the grating screw anti-clockwise about 1 turn until the signal on the oscilloscope is minimal. Put on the 8-inch test disc and search for a black picture. Adjust the amplitude of the signal from the signal generator so that a 1 kHz tone is just audible and the oscilloscope displays an HF signal modulated with a 1 kHz sine wave. Loosen the fixing screw slightly and adjust the position of the photodiodes until the amplitudes of the modulated HF signal are symmetrical. Fasten the fixing screw again. 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 Again.